We're going to finish the problem, but we're going to hop right into the dimensional scaling. So, the given. This is all the information you're given. You're given for the Earth's crust and also for your wax model. Now, what's the first problem? Part A, they're telling you to do how many dimensionless groups are there. So how many parameters do we have? 7 parameters, and we break those parameters into their dimensions. Now, energy, does that count? Is energy a dimension? No, because energy can be broken up into work, and work is force times distance. So then you break it up into your SI units and then your dimensions of m times L squared over T squared. So remember to do that. I know some groups thought energy was a dimension. Okay, so you have 7 parameters, right? Now when it says Tm minus Ts, that's just one parameter. So you have 7 parameters and 4 dimensions. So you have 7 minus 4, there's 3 dimensionless groups. How many of you guys got 3 dimensionless groups? All right, okay, everyone, so that's good to see. All right, so now you've been doing this all discussion. You just work through the typical method to find what are the dimensionless groups in the system. So you create your general equation for a dimensionless group. You take all your parameters and you put them to their exponents. Then you substitute the dimensions for each parameter, like thus, and then you work to find each dimensionless group. So in order for the group to be dimensionless, the exponents must be 0. So you write your equations for each dimension, for mass, time, temperature, and length, and this is what you get. Now there was some confusion on what is a core variable. Basically, if the problem states that delta H is the core variable, and you know that there are 2 other core variables, and you have 3 dimensionless groups, one dimensionless group must have delta H in it, and the other 2 core variables are not in that dimensionless group. So you know there's delta H, but then the other 2 core variables, you can set their exponents to 0. So we are instructed to use delta H, K, and V as the core variables because we have 3. Now you eliminate V and K based off the problem, and you know delta H is in the core variables, so that gives you 8, and then you solve through the method that you guys are all familiar with, A is 0, B is 0, C is 0, and so forth. So your first dimensionless group is delta H melting over Cp times delta T. Now, you guys have seen these parameters before, Gen Chem, right? If we multiply the numerator and the denominator by mass, that would just be m times delta H, which is the energy required to melt the solid. And the bottom, you have mc delta T. That takes you guys back to high school, right? And that's just the energy required to heat the solid from one temperature to the next, from the surface temperature to the melting point. So this dimensionless group that you found is really the ratio of 2 different energies. So it kind of makes it's really, even though this looks foreign, it's a dimensionless group, what's that? There are things that you've seen before. So similarly, we found the other 2 dimensionless groups. For dimensionless group number 2, we know K is in it, and delta H and V are not. So that's how you substitute in 0 for 2 of the parameters, and you solve for the other variables. Now, traditionally, when you're working with dimensionless groups, you don't like to have fractions in your exponents. Back in the day, when they were first doing dimensional analysis, they didn't have calculators. They didn't have other tools to do calculations, like MATLAB or computers. And so squaring a number is much easier than finding the square root. So when you're working with a dimensionless number, you usually you want your exponents to be whole numbers, so they square the numerator and denominator there. And then for the 3rd dimensionless group, they did the similar method, squared the numerator, squared the denominator. So what are we looking at in the 2nd dimensionless group? Well, if you move the height and the density up to the numerator, so it's K over HP quantity squared, and then you have Cp and Tm and Ts in the bottom, you're really looking at the heat transfer. The numerator is related to the heat transferred through the crust, and the denominator is, again, the energy required to heat your solid to the melting point. So again, it's the ratio of 2 different energies. For the 3rd dimensionless group, you have V squared, and you have Cp delta T again. Now, if you were to multiply the numerator and denominator by m, what does mv look like? What kind of energy? Kinetic energy, 1/2 mv squared. So the numerator is related to the kinetic energy of the plate moving, so it's moving very slowly. So the kinetic energy over the energy, again, to heat the solid. So as you see, the denominator is similar in all the dimensionless groups. So we have the dimensionless groups, and so now we can do the scaling to compare professor's model to what actual plate tectonics are like in the Earth's crust. So for part C, we start with we use the first dimensionalist group to determine the delta T for your model. So they give you all the information, and you also know that the delta T that the professor uses is 50 degrees Celsius, but you want to see what is Tm minus Ts if we just solve exactly using all the parameters that we do now. So you solve for Tm minus Ts for the wax model, and you know all these parameters, you just plug them in, and you get 430 degrees Celsius. So does that seem like a large delta T to you guys? So in your model, in order to have a similar dimensional scaling as real life plate tectonics, you would need a temperature difference of 430 degrees Celsius. So let's see, is this even possible? So the melting point of wax is 7 degrees Celsius. And what's the coldest that we can be? Or actually, theoretically, what's the coldest temperature? Absolute zero. Negative 273 degrees Celsius. So absolute zero, 0 Kelvin. That's the coldest we can get. So the largest theoretical max temperature difference we could get is 343 degrees Celsius. But in order to model real life using wax, we would need 430. So based off this analysis, well, you're thinking, well, it's not possible. This the temperature difference required cannot be achieved currently. We go through the similar dimensionalist groups using the temperature that we found in the first dimensionalist group. Same method of solving. We get the height of the wax needs to be 4.5 kilometers, and the speed of the wax needs to be 7.7 times 10 to the negative 10th meters per second. Now, does anyone know how many miles 4.5 kilometers is? Around 3, right? So 4.5 kilometers is around 2.8 miles. So if you compare that to for some perspective, the Earth's mantle is 2,900 kilometers, so that's around 1/1000th thickness of the Earth's mantle. And the plate velocity in your model would be slower than the Earth crust actually spreads. So really, you would need a tremendous amount. Think of that, 2.8 miles vertical distance for the height of your wax. Yeah, that's not happening. So based off this analysis, the model is not dynamically similar. So you might think, oh, well, this professor, maybe that's why he had to leave. Well, let's look into it more. So what we're about to do is an analysis that kind of goes outside the scope of this class. But are all the dimensionalist groups important? Let's take a look. So if we look at the Earth, and we have the 3 dimensionalist groups, we plug in the parameters known for the Earth's crust and mantle, and we get the first dimensionalist group's 0.2, whereas the other dimensionalist groups are significantly smaller. That's tiny. That's like Avogadro's number status. That's tiny. So the first dimensionalist group is really the important dimensionalist group, 0.2. When you have a dimensionalist group, in order to be significant, it needs to be within like a tenth to 100 or up to 100. And so these fall outside of importance. Now if we compare the first dimensionalist group for wax, using the choices that the professor made, which is 50 degrees Celsius, we find that the first dimensionalist group is around 2. So really, if you compare the dimensionalist group of the wax system that the professor did compared to the Earth's, it's only 10 times greater. So it's pretty similar. So even though by inspection when you first did the problem, this is not possible, they're not dimensionally similar. If you look a little bit closer, further analysis, well, 2 compared to 0.2, that's pretty close. Now if we look at the other dimensionalist groups, they're tiny. Well, let's take a look at them anyway. So Earth, if we did the ratio of the second dimensionalist group over the third dimensionalist group, we get 2 times 10 to the negative 4th. If we use the information that's provided by the professor, 10 millimeters per second, that's how fast the wax moves, you get a dimensionalist ratio of 2 times 10 to the negative 5th. So comparing the wax model to Earth's, these ratios are actually pretty similar. So upon further inspection, the model that the professor used and to model Earth's crust, they are dynamically similar. But at first glance, which is all that's required of you guys in the scope of this class, it is not dynamically similar, because you would need ridiculous height and a temperature difference. Any questions?
So it's not.
So they are, but they're not.
So the answer on your homework would have been it's not similar, and that would have been the correct answer, because that's the limit of in this class. But if you look farther, you'd find out this professor didn't choose Duncan because he was looking at ratios of energies that are insignificant, should not even be in the on the exercise. Great, thanks everybody.